Friends, today we'll be talking about different welding processes. Those are used in aerospace grade welding. As you know that we use very exotic alloys, very thin cross sections and very lightweight alloys to control the weight and to have the maximum strength, that is strength to weight ratio is the highest in all our designs, choice of materials, and also the way we manufacture or fabricate. So there are basically two different kinds of processes we use in aerospace. One is the arc welding process, other one is the resistance welding process. And in arc welding, even though there are four major categories of welding, like shielded metal arc welding or a stick electrode. Second one is continuous wire, which is fed through CO2 atmosphere, carbon dioxide atmosphere, or argon or helium gas, a solid wire or a flux core wire, FCAW or a GMAW, flux core arc welding or gas metal arc welding. Or we have a submerged arc welding, which is extension and modification of stick electrodes, where electrode length is finite, and here in submerged arc we use continuous rods, coils of very high weight, more than 12 to 50 kilograms of the wire spools are loaded onto the machine, and along with the wire, instead of flux getting coated on top of the wire, there is a flux which comes through a hopper, and it is continuously fed along with the wire into the weld joint. But this process being used for mainly very high thicknesses. In aerospace we don't use it, and since the arc is fully submerged into the flux envelope, it is called as a submerged arc welding, but we will not be considering in our today's discussion. So there are three important processes. The stick electrode, which used to be very widely used in earlier days, but in last 3 to 4 decades even this stick electrode welding is also not being used, and that is where, even though it's a very versatile, very convenient, low cost process, today aerospace cannot afford to have, because most of the time we are finding that this process will add sometimes slag inclusions, and it is good to have where a lot of fill-up is required, rather than controlling weld to a very thin sections of 0.6 millimeters to 8 millimeters, and a good control over penetration, single-sided joints which cannot be accessed very easily from the other side. And in such cases, submerged arc welding or stick electrode welding is not feasible, and today's demand on our quality, the reliability, the airworthiness for each of our product is so high that nobody will risk, after having spent quite a good amount of money in machining of complex components. So considering this, we are left with only two important processes: the process of TIG welding or gas tungsten arc welding, the more correct technical name. In this, the tungsten electrode is clamped into a torch, either gas cooled or water cooled, depending upon the diameter of the tungsten and the current of the joint or the process, the WPS what it specifies. And this is a non-consumable electrode. So unlike all other arc welding processes where the electrode itself creates a source of heat and source of filler metal, this is the only process, gas tungsten arc welding or a TIG welding, tungsten inert gas welding, where we actually don't burn the electrode. And like a gas welding, we will be adding filler wire. So there is a torch and the filler wire is added into this as we proceed on to the weld joint. Now the second process, which is now coming more and more into the usage after the electronics in welding has entered, and trying to improve upon the characteristics of the welding current, and the synergic welding or the programmable TIG machines or programmable MIG machines are really made wonders in improving the quality of the welding. In addition to having a arc which is struck and stable at very low temperatures, or having a different pulsing possibilities. A normal sinusoidal wave with superimposition using the electronic circuits can be converted into a square wave, and once you have a square wave pattern, then you can adjust the positive, negative, and then many permutation combinations can be worked out in such a way that you get actually one droplet, or one droplet from the filler wire, you actually add it in one pulse, fuse it properly, and then go for the next one. And that gives a beautiful control to a welder, both in manual as well as in auto welding possibilities. So that's the beauty of these two processes, and thanks to electronics and means to actually monitor, control online voltage, current, with using different sensors, and have a feedback. It's a closed loop, like we have a CNC machines, and the current actually, or rather I will say the heat input into the weld is manipulated, controlled. And this is the beauty of the TIG or the MIG welding using this advanced electronics, that today we can actually use different, more than 999 sectors in welding a joint, and especially the jobs or odd shaped jobs which are not very easy to rotate or move. There the jobs are stationary, and then you need to move your torch across the joint all through 360-degree, and in doing that you will be cutting across various positions, and certain welding positions like 1F, 2F and 1G, they are assisted with the gravity, whereas in 3G you have kind of a neutral when you are doing horizontal welding. Yes, there is a gravitational force, but it's not helping in very high effective way in 1G, 1F, 2F positions, or it is not as detrimental as when you are going to do overhead welding using 4G positions. And if the jobs are quite large and not rotatable, movable, and they are all going across 360 degrees, then you will end up into 5G, 6G positions. And in such cases, this tungsten gas welding, which has advantage of the source of heat, that is the tungsten electrode which strikes a arc, and the filler wire which is separate, can then use to manipulate the weld joints very well and achieve both good fusion, penetration, and the profile of welding. Purging from backside is of course mandatory in such cases, as there is no flux, and you need to really protect some of the materials like what we discussed in our earlier sessions, titanium and stainless steel, which are very high prone, or aluminum, for interacting with oxygen from the air. So proper purging systems to protect weld from the other side are also essential. Now these are some of the important points of these processes. Now let us talk about what happens when we have automation. I mean, when the production requirements are very high, the MIG welding is the easiest process, or the flux core arc welding is the easiest process to automate. Similarly, tungsten, where you don't require filler, you are actually going to fuse the parent metal itself, and it is called as autogenous welding. So TIG welding is also very easy to automate it. But when you have filler wire in the TIG welding process, then it becomes difficult to automate. And as a result, what happens is, then you require sophisticated robots and additional axis on these robots, where you want the wire feeder and the angle in which the wire is brought in inside the welding also to rotate depending upon the movement of the torch and the shape of the product or the shape of the article being welded. So what is done is today is that we have different means to automate it, and the simplest part in TIG welding automation is to use an old lathe, hold your job onto the lathe if it is circular, or if it is a longitudinal, and just use the motion of the bed instead of the cutting tool, you mount a torch there and you reduce speed drastically. In machining, we use very high 50 to 100, 200, and in many cases even 1000 RPM. Whereas in welding, our surface speeds are going to be something like 50 to 100 millimeters per minute, so a point 1, point 2 RPM. So heavy reduction in these motors are required using a gearbox so that you achieve a slow speed but uniform speed. The idea of using lathe is that it has very high accuracies as far as the rotation is concerned, the center accuracies, and the torch movements which are required to move left and right, up and down. These are all possible on the welding lathe. One can design a separate welding lathe also. The second way of automation is using robotic welding, where you hold a torch into a robo, or vice versa. You hold a part into a robo and torch is stationary, and you create a relative movement between torch and the product. The third is called as a orbital welding, and in this you have a stationary pipe and a raw tungsten gas envelope moves across this entire pipe in a very close manner or open manner, depending upon what kind of torches and the guns you have selected. Now that helps in creating very accurate weld joints, and something similar to what otherwise we would have spent heavy money on to electron beam welding or a laser welding. Something similar to that can be achieved using TIG welding if you do this kind of automation, and it saves lot of money. Infrastructure cost also comes down, and you are very quick to finish these welds. However, you have to have a very precise control on the weld joints. Unless and until the weld joints, like in EB welding, everything is machined, and even the fixture which you are going to assemble this is also a very highly engineered tool, or it's almost like a machine which is firmly held the job into a right tight control, and then gives to beautiful welding into EB welding. So these are the different kinds of techniques which are used as far as the TIG welding is concerned. Now in TIG welding there are a few precautions which are required to be taken. One is that there is a pre-slope, there is a upslope, there is a standard current or a pulsing current, or then you have a downslope, and then there is a post flow. So all these parameters for aerospace grade welding are required to be controlled, and before you strike a arc you have to create sufficient amount of argon or helium or a neutral gas envelope, and that is where the first pre-flow is required. Then as you strike a current, in TIG welding, since tungsten electrode is a non-consumable electrode, you cannot actually touch to the parent metal. So we impose a high frequency on top of it, and this high frequency actually transfers arc without touching tungsten electrode to the parent metal. So this technique is required to first get energized, and then the arc jumps, you get an arc, and then you have upslope, slowly current starts increasing to your peak value. As it reaches there, either you have sinusoidal, square wave, pulsing, non-pulsing currents, and then once your joint is complete, then to fill up the crater you have a good downslope, so that you keep on filling up that crater which comes up, and there you add small amount of filler metal, little excess than the other, and later on you can dress it up so that your crater is always completely filled, and the last shrinkage cracks are not actually come into your weld joint. The second difficulty in TIG welding or tungsten inert gas welding is that it requires a costly tungsten, requires a very good sharpening device, so that you have every time accurate angle in which you will be able to sharpen it or blunt it. For aluminium in AC welding you require it to be blunt, and then you hold this tungsten electrode and the filler wire in such a way that the envelope which is coming of the gas, the wire can be at different angles. I mean, one can insert a wire at very straight 70-80 degrees, or one can enter it at 10 to 15 degrees, but the ideal angle is about 20 to 30 degrees, and you have to push this wire in such a way that it goes into the arc for a time that which give you size of weld puddle or pool, which you move it and ensure that it gets properly fused, and then you call for one more. But when you withdraw your wire, the wire still should be within the argon atmosphere or the inert gas atmosphere. It comes out from the arc, but it doesn't come out of the argon or the neutral gas which you are using it. So that's the important part, and that gives a very slow speed for this. So that is the limitation. The deposition rates in these are very less. The speeds are also, normal speeds are between 25 to 50 to 60 millimeters per minute. If you use really very heavy tungsten electrode of 6 millimeter or something like that, and very nicely designed water cooled torch up to 400 amps or 600 amps, then only you can use filler wires of more than 3 or 4 and try to deposit more and cover up the joint faster. Otherwise, most of the time TIG welding you will see 1.2, 1.6 or at the most 2 dia. These 3 diameters are very famous. 1.6 of course has the peak, and maximum utilization of tungsten welding happens using 1.6 millimeter diameter of wire, about 1 meter in length. But now, as I said earlier, there are automation possibilities, and when the automation takes place, you use a continuous wire, and when you have a continuous wire, few modifications have come up to improve the deposition rate by heating the wire before it comes into the weld puddle. So instead of feeding the wire at ambient temperature, you actually raise the temperature by resistance heating of the wire to 400, 600 degrees centigrade, till the time wire still becomes stronger to get fed. Otherwise it will start losing its properties and sag, and then feeding will become difficult. So it's not that very high temperature, but at least 2-3 degree 400 degrees centigrade you can save heat from the arc, and that much more deposition, that much more wire you can feed and use the extra heat available in the parent wire for melting. The next level of difficulty in TIG welding is that it requires a very large setup, a power source, a water cooling tank, a gas cylinder, torch, and then various other means to have upslope, downslope, high frequency units, and that makes it little more cumbersome as far as the setups and movement of this machine from one place to other place. Operating on sites in the open atmosphere, open environment where there is a wind, the gas doesn't stay, shield gets disturbed, and then you cannot weld. So there are some limitations, but otherwise it is one of the finest and the best process for going into the aerospace welding. So this is as far as TIG and MIG welding is concerned. MIG welding of course is mainly used in automation in aluminium and larger thicknesses, where thickness goes beyond 8 to 10 millimeters in aerospace. Then MIG welding is preferred, or in the case of aluminium where you want to have very high properties, because MIG welding gives the least heat input for the same amount of material what you are depositing onto the parent metal. I think let us move from this to the resistance welding. The resistance welding is, once again, there are two types which are used in aerospace industry. First one is of course the spot welding, where you have two copper electrodes and you pass low voltage but very high current, low voltage of 15 to 20 volts, but currents of ranging up to thousands of amps is passed through the electrode, and two plates to be joined, they are fixed between the electrode. And what happens actually, even if we see that it is perfectly butting, but if you apply glue, you will see only few spots the plate is touching, and especially between the two electrodes, the areas between the two electrodes is not fully touching each other. So rest of the air gives a very heavy resistance, and the current starts flowing only through these small areas of contacts there between the two plates, and that increases the current density, and current density then helps in melting localized regions, and at the same time you are applying pressure on the tungsten electrode. So when the pressure is applied, more and more contact area comes in, plus because of pressure there is increase in temperature also, which melts and helps in forming a good nugget, a small area. If you chisel it out after the spot welding, you will see a small area being fused between the two parts, and this is actually a area of quality where we have to achieve constantly the right nugget size, right diameter, right profile of this nugget, and that is one of the destructive tests which is done on this, in addition to the chisel test where you separate out two lap areas. And the second version of this process is, instead of discrete spots which are being given, you have two rollers under which you pass the plates, and these rollers are actually carrying the current. So these rollers are also made out of copper so that they don't get heated up because of their good conductivity, and the part which is coming between the two rollers, where a continuous line can be established, comes in and forms a beautiful weld. Once again, these processes, as you know, requires very sophisticated machines if you want to have the nuggets and the fusion lines controlled to various parameters. There is a heat affected zone because there is always heating up of the plate when it melts, but most of the time this welding is done under water. That means you have a continuous flow of water, like we have flow of argon in tungsten electrode. Here continuous water is being sprayed to take away heat and protect copper. Maybe there is of course an internal water cooling arrangement also in some of the machines it is provided, but external water cooling is required for protection of the parts, distortion levels to be monitored, and overall benefit of the process. So that's a summary of the processes what we are doing it, and thank you for watching. We will see in the next episode quite soon. Thank you.